We're going to start today by looking at real numbers and number operations. The first thing we're going to do is cover some vocabulary, and it's going to be our subsets of the real numbers. The first one we have is what you start out when you're really young, and it's your whole numbers. It would be 0, 1, 2, 3, 4. And these three dots right here indicate that it goes on forever in this direction. So it would include 5, 6, 7, 8, and it just keeps going forever. We also have the integers. Now, you didn't learn about the integers until you were probably in upper elementary school. We still have our whole numbers here, but notice with integers it also starts to include negative numbers. And again, these dots mean that it goes on forever in that direction, and it goes on forever in that direction. Now, our rational numbers. The key here with rational is the root word. And the root of rational is ratio. And a ratio basically means it can be written as a fraction. So a rational number is any number that can be written as a ratio of two integers. This just means it can be written as a fraction. Now, our rational numbers can be in the form of decimals, because if we have the decimal 0.5, we can still rewrite that as a ratio of 1 to 2. Repeating decimals can also be written as ratios. Fractions. Now notice these integers and the whole numbers. They can also be written as rational numbers, because I can write 4 as 4 over 1, and that's a ratio of two numbers. So a rational number is a ratio. It can be written as a fraction. About the only thing that can't be written as rational that we'll deal with would be square roots that are not perfect, so like the square root of 2, and non-repeating, non-terminating decimals. And then our last one is irrational, and basically irrational is anything that doesn't fall into the rational category. So it's a real number that cannot be written as a ratio. Okay, now we're going to look at a little diagram to kind of show you how the subsets all interact with each other. So if we look at this first big blue rectangle, we're just going to call that numbers. Now, within our idea of numbers here, we've got two major sets we're going to be talking about, and we're going to be talking about real numbers and imaginary numbers. Now, the imaginary numbers we aren't going to talk about today. That'll be at a later time. But just realize that numbers are divided into real numbers and imaginary numbers for us. Well, once we get inside the real numbers, now we can break the real numbers down into two other categories: the rational numbers and the irrational. Now remember, rational means it can be written as a ratio. So these are anything we can write as a fraction. This is anything that's not a fraction. We're going to break our rational numbers down a little bit farther, and that's going to be into the integers. Now remember, the integers are like -3, -2, all the way up to 4, 5, 6, and they keep going. So those are our integers. Then we can even break the integers down a little bit farther, and that is into the whole numbers. That's 0, 1, 2, 3, 4. So what I'm going to do now is I'm going to kind of give you a little bit of a different scenario, because it can be hard to understand how these all interact. So let's say instead of numbers we have animals. And maybe we want to look at the two subsets, mammals, so that would be like our real numbers, and birds. Could be another subset. So what you have to realize is that mammals and birds both classify as animals, but they're two kind of smaller categories of animals. Same thing with real numbers and imaginary numbers. Now if we go over here, if we look at the mammals, maybe we're going to talk about dogs, and that would be like our rational numbers, and maybe our irrational would be cats. So dogs and cats are both mammals, which are still animals, and that's the same thing for your rational and irrational. They're still real numbers, which are still numbers. Now if we go one step farther, maybe our integers is a poodle. Well, a poodle is still a dog, which is still a mammal, which is still an animal. Integers are rational numbers, they are real numbers, and they are part of the number system. And let's say we break this down even a little bit farther, and let's say you have a poodle named Sally. that would be like our whole numbers. Sally is a very specific poodle, but she's still a poodle, still a dog, still a mammal, still an animal. Same thing with whole numbers. Whole numbers are still integers, they're still rational, they're still real, and they're still numbers. So hopefully that helps you understand a little bit better how these subsets all interact with each other. Now we're going to quickly review the number line. So here's the problem we're going to do. It says categorize, order from smallest to largest, and graph the following numbers. Let's deal with the categorize first. This goes back to the idea of this diagram here. We have to decide what categories do these numbers fall into. So when we categorize it, if we start with the number 3, you might look back on your diagram and figure out, okay, where does the 3 fall in? Well, the most specific thing that we could call a 3 would be a whole number. And since it's part of the whole numbers, that also means that it is part of the integers, the rationals, and the reals. Now with the negative 2.3, that is not a whole number because it has the decimal. It's not an integer because it has the decimal part. Well, since it's a terminating decimal, you can write it as a fraction. It would be negative 2 3/10, and then you could change that into negative 23/10. So this one would be rational and real. Now the same thing for the 1.7. It's a terminating decimal, so that puts us at rational and real. Now the negative 1/2, that's already written as a fraction for you, so you don't have to ask yourself if you can write it as a fraction. You just have to ask, can it be more specific or anything like that? And it's the exact same thing as this 1.7 and the negative 2.3. It would be rational and real. Now the square root of 3. Well, since the decimal keeps going and it doesn't repeat, doesn't have a pattern, it doesn't terminate, that means it's irrational. It cannot be written as a fraction. So the square root of 3 would be an irrational number. And then this negative 4 might look like it could fall in the whole numbers, but it does not because of the negative sign. We can include it as specific as the integers though. So it would be the integer, the rational, and the real. So now we are going to order these from smallest to largest. What I need to start thinking about is small numbers. I need to think about those negative numbers. And the smallest number I have is negative 4. If you think about it in terms of money, negative means you owe. Well, owing $4 is you owe more than if you owe $2.30. So we're going to have a negative 4. Negative 2.3 would be next. Now this negative 1/2, because it's still a negative. And now I've got to jump into my positive numbers. Now you got to be really careful here because obviously 3 is bigger than 1.7, but this is square root of 3. Hard to compare when I just leave it like that, so I want to put it like that decimal. But got another problem. I have 1.7 and 1.7. Well, the square root of 3 was actually like 1.72, something like that. So we've got to take it out a decimal farther, and you've got to ask yourself which one of these numbers is smaller. If you think of it in terms of money, this would be like having $1.70. This would be like having $1.72. Well, the $1.70 is smaller. So we would do 1.7 next. Now, we're not going to write down 1.72 because that's not actually my original number, my number I started with. We're going to put down the square root of 3. We had to change it to a decimal so we could compare it, but that's not actually the number. We always use the original form of our numbers. And then last is 3. Okay, so that takes care of our categorizing, our ordering from smallest to largest, and now we have to graph it. And now when I plot my numbers, negative 4, I'm going to go over here and put a dot at negative 4. Negative 2.3, I go negative 1, I go negative 2, and then I go 0.3 farther, darn it. Negative 1/2, I go halfway between negative 1 and 0. And then the 1.7, I go 1 and then 7/10 of the way. And then the square root of 3 was also 1.7, so you're going to put a second dot right by it. And then 3. So there we've gotten that problem taken care of. Hey, the last thing we have to talk about are different properties of addition and multiplication. Most of these you've seen. The first one is possibly a new one for you. It is called the property of closure. And it might seem a little abstract what this property even means, but when you get into higher level math, it'll make more sense the purpose of it. So what this tells us, our property of closure says that if we have a real number, A and B, so A is real number and B is real number, if we add them together, our result is going to be a real number. So if you think of that diagram we did where we had real numbers over here and we had imaginary over here, remember I told you we're not talking about imaginary yet, that'll come later. What they're saying is if I take a number from the real side and another number from the real side, their answer together is still going to be on the real side. It will not jump over to this imaginary side. Same thing with multiplication. If I multiply these two real numbers together, I'm going to get another real number. Our commutative property basically says when we have addition or multiplication, it doesn't matter what order we add them in. I could do A plus B or I could do B plus A. Same thing with multiply. A plus B is equal to B plus A. If you think about commutative, the word commute, people go from home and then they drive to work. Well, they probably take the same route when they go from work and drive back home at the end of the day. So it's letting you flip them around. Associate property. For addition, if I have three numbers that I'm adding, A, B, and C, I can add A and B first and then add C, or I can add B and C first and then add A. It doesn't matter with addition who you associate with first. So this one, B is associating with A first, but in the second part, B is associating with C. You'll still get the same answer with addition, and the same thing with multiplication. Now, identity. If you think of your identity, like your driver's license, what this is saying is that if I add a 0 to something, I get the same thing back. So just like on your driver's license, you are on your driver's license. You start with you, and you end with you. Now for multiplication, it's not 0, it's 1. If I take any number times 1, I get the same thing back. Now our inverse, a lot of times inverse is closely related to the term opposite. For our additive inverse, it's saying if I take a number and add its opposite, I'm going to get that identity number back. So if I take -5 and I add its opposite, I'm going to get back my identity. I'm going to get back that 0. Now with multiplication, it's slightly different. If I have the number 2, I have to multiply it by 1/2 in order to get my identity back. Or if I had the number 2/3, I would have to multiply it by 3/2 to get my identity back. So with multiplicative inverse, it's the reciprocal of each other. And then the distributive property actually combines addition and multiplication. If I have a number on the outside of a set of parentheses that's being multiplied, I can distribute that to the inside and have an equivalent expression. So notice the plus sign stayed, and then I have A times B plus A times C. Okay, what I want you to do now is pause the video, and I want you to identify each property that's shown here. Okay, the first one is the commutative property of addition. I went from home to work and then work to home. And the reason we put down of addition is because it was using addition. If this had been a multiplication problem, it would say the commutative property of multiplication. Number 2, this one you might not have recognized. This is actually your additive inverse. Because with a minus sign, what that really is, it is adding the opposite. So we take 9 plus -9, and that gives us our identity. That should have been the key for this one, was that it equaled our identity. So that's our additive inverse. Number 3 is our distributive property. Distribute that 8 out. Number 4 is the associative property, and it's the associative property of multiplication because it's a multiplication problem. And the last one, again, we ended up with our identity, so this is our multiplicative inverse because it was a multiply problem.